of all old materials. Okay? So what I suggest is when we take a test, and when I get the test back, I'm going to go through and give you the correct answers. So you can put the correct answers on your test. Okay? You're going to want to study those, obviously, for the final. 70%. You have to have 74 on the test, right, to pass. So at least if you got old material, you know you're at 70%, correct? The last 30% is on case studies. So everything that we're learning, you're going to have to put into a case study or into it. And in all honesty, everything's multiple choice. But anyway, but I'm just giving you a heads up. So if the day I get the test back and maybe you're not here, make sure you get the right answers from somebody else. So because that's what you're going to want to study for the final. Okay? So not any really big surprises. And then I do have a sheet towards the end where I tell you how many points come from each test. Does that make sense to you? So that you're like, you know, not studying this test and only this test to find out, well, there's only 2 questions from it. Does that make sense? That's right. You'll be okay. All right. We're doing instrumentation, and then we're going to do a safety data sheet. So if you didn't pick up a safety data sheet, they're up there. We're going to do that worksheet together. And then we're going to go over to the lab, and we're going to do a pipette calibration. Yes, that's what we're going to fill out. So today is instrumentation, global harmonizing system, just a data sheet. You're going to give me your presentation, have your presentation, and we're going to do pipette calibration. So what did y'all decide on test 7? Are you going to share, or are you guys just do it on your own? Maybe pick your page and then you can share.
We're kind of waiting for maybe to get together.
Oh, I'm not pushing. You guys do whatever you want to do. I'm just saying. It's a bear. It is a bear.
You guys want to do that now?
I printed it off and
I read for I
And again, I don't want you to give each other the answers. Right? When you find the answer, what are you going to do?
we're right down where I found it.
Where you found it, like what PowerPoint, maybe what slide on what PowerPoint, or if you found it in the textbook, what page in the textbook, and then just try to give them just that information. And then if they can't find it from then, maybe you've written it down wrong or something, then you guys can talk about it. If you leave me with 73 questions or whatever, you're going to be doing a lot of reading and a lot of PowerPoint stuff anyway. So. Okay, I'm going to run through my portion real quick, and then I'm going to step aside. And you all are going to tell us what you know. And you can stay in your seat. You don't have to get up here. Unless you want to use the Elmo or the computer or something, that's fine. But if you don't want to, you can stay at your seats. Well, I guess you can. Yeah, you guys can. Okay, so. Told you I had to teach you everything that you needed to know about the spectrophotometry. Photometry falls under Beer's law, where the absorbance of the light is equal to 2 times the negative log of percent T. That's basically what Beer's law says. A is your absorbance, T is your transmittance. So what it's basically saying to you, it is a mathematical expression of the relationship between the absorbance of the light and the transmission of light. That's all it is in that big equation. Okay? On your test, all you're going to do is find the equation. Okay. So we did the spectrophotometer yesterday, correct? We probably did them a ton of times in hematology. So it's your best friend, I'm sure. We did a band pass yesterday. Can anybody tell me exactly what the band pass did? What did you do? What did it tell you?
Better stuff.
Well, but what was the reason for doing it? What did you want to see?
I wanted to see more of a gap between 20, like the middle.
So we had kind of a nice bell curve, right? Ours were pretty wide, but what do you want to see? You want to see like a spike, right? You want to see where that absorbance is, where your top is, and that's what you want. The narrower that band, the better your spec, right? Tells you the quality of your spectrophotometer. Measures the light transmitted by a solution, determine the concentration. So when we do this in lab, you did it with your hemoglobins, right? You put your blood in there, and the less light that went through meant your specimen was what? Because we're dealing with anemia or polycythemia, right? That's what your hemoglobins are telling you. You're either anemic, which means you don't have any blood, or you're polycythemic and you have too much. So if you don't have any light going through, what is that telling you? Your specimen is high. How much light shines through mud? None, right? How much light shines through water? A lot. So if you're anemic and you don't have any blood, it's basically shining through water. You get a lot of light on the other side, right? But if you got polycythemia and you don't get very much light, inverse relationship, right? Percent transmittance or the absorption of light is what's measured. Yesterday we measured the percent transmittance. That was the needle, the scale on the top. Today with the pipette calibration, you're going to be reading absorbance. That's the scale on the bottom. Okay. I told you yesterday that what we did yesterday is part of your practical. What you are going to do on your practical, you are going to pick a standard. I'm going to tell you which one to pick. So let's say the 420.5. You're going to go into the thing and you're going to pick 420.5 that I tell you. You're going to zero the instrument. You're going to blank the instrument. You're going to put that standard in the instrument, and you're going to tell me what is the transmittance and what is the absorbance. That's it. Okay? The other thing you're going to do for me on your practical from your lab yesterday, I'm going to tell you that you're buying an instrument that has a band pass of 30. You're going to draw this. Give yourself some numbers. 0 and 100 and halfway is 50. My band pass is 20. And we'll go over that. So what are the parts of the spectrophotometer? You have the light source. You have the monochromator, diffraction grating. You have the cuvette. That's what holds your specimen, the detector, and the readout device. So we'll go through each one of those separately. So the light source provides your radiant energy. What you need to know from me is it's a tungsten lamp. We are dealing with visible light. We are not doing any of that CSI stuff, right? We're just looking for specimens, okay? So most spectrophotometers that we're going to be using are going to be using a tungsten lamp. My CA240, my Phobos Mira, and the little ones in there, just use tungsten. If we were doing CSI stuff, we could either do it, however you pronounce that word, and mercury lamp, okay? Different choices, but again, tungsten lamp, visible lamp. So this just kind of gives you a little bit more information on the light source, what range you're working in. I can't remember it. In the very back. Yesterday you had a problem. When you put yours in, you were like, Barb, it went way off scale.
Yeah,
And what did I have to do for you?
that little lever on the bottom.
Right, and what was that little lever doing?
Changing the coordinate.
Exactly. So again, that's if you're running into a problem when we're doing a manual procedure, make sure that whatever wavelength you're running for that procedure, that little knob is turned over, because it just gets knocked every once in a while, it gets swung over. And so something you want to pay attention to. Okay. If you notice, visible light, 380 to 750, which is again what we're going to be doing. What cuvette are we using? And what did I tell you borosilicate was? In yesterday's lecture.
Cheap glass.
Cheap glass, that's exactly right. Cheap glass, that's that throwaway pipette, or test tubes that we're using in class. Okay, cheap glass. I do have some actual quartz cuvettes. We actually found them when we were cleaning the lab. With the quartz ones, you don't throw those away. Those you have to rewash and, put them away. So Jean's like, well, you can play with them until they're scratched up and no good anymore, so we did find some. We do have some. I'll use them once we just throw away. So the monochromator is the device that isolates your radiant energy to the desired wavelength that you need. So what did we play with yesterday? What were we turning? What were you changing? You had your specimen in the window, in the spec. What were you moving? What were you doing? Changing your wavelength. Okay. So, in essence, we were doing a band pass, right? Describes the spectral purity of your monochromator. So a monochromator, you can have several different kinds. A colored glass filter, least expensive. Interference filter, a prism. So if you're looking at, you have a prism, anyway, you know what a prism is, right? A piece of glass. And you hold that up to the light, what happens to it on the wall?
It splits the light.
It splits the light, and what do you get? A rainbow, exactly right. So again, diffraction waves. The most common one, and the one that we have here, is basically a glass slide with etches scratched in it. And as the light goes across that glass slide, kind of acts as that prism and spreads out your light into the rainbow. Okay? And those are the most common, and the one that we have here. Cuvette, you know what a cuvette is? It's what holds your specimen. A true cuvette, a quartz cuvette, has that little symbol on it, as good as I can do with a computer. And so when you decided how to put your specimen in hematology into the spec, did you have to do anything special with that cuvette, with that test tube? No, you just wiped off your fingerprints and stuck it in, right? But if you're using an actual cuvette, has that symbol on it, that symbol has to be facing you so that the angle of the light going through is always the exact angle. Does that make sense? Okay, so that's something we'll look at with a cuvette. Your photo detector just collects your light. Then you get a readout device, and your readout device is just that little needle, right, on the spec that tells you. And what's the recorder? You, right. Now, when you do, we're going to do pipette calibration today. You're going to be the recorder. You're going to do this in the lab. This is required. You have to do pipette calibration every year. It is required. But now they are kind of simple, a little more simple in that when you put it in, it actually prints it out like a little calculator. So you have a little piece of paper, then you actually have something you can staple to it and prove to the inspectors that you're doing it. So you actually have a readout device. But for my machine of little brain, it is just you. Okay, so wavelength accuracy. We used a Hallam oxide glass filter. That's what we used yesterday. That's what those were. Okay, and we just used the selector and we found out the accuracy of our wavelength. Stray light. How do we prevent stray light? You have to close the lid, right? Exactly. Linearity. Okay, linearity. I'm going to beat you up over linearity. We're going to talk about linearity a lot. So here's your first introduction. Okay. You did hemoglobins and you made a curve, yes? Mm-hmm. And let's say your low number was a 5 and your high number was an 18. Let's say. And you drew a line. right through your points. Am I right? Okay. So you put your specimen in and you got a value of, say, we'll say 5, and you got a value of 18. But did you stop between those lines? What did you do? She told you just to draw a straight line and tell you where to start or to stop, right? Okay. In chemistry, we have lines, if you will. We have a graph, all right? But in chemistry, if the 5 is my lowest number, can I report out anything less than 5? Is it accurate? No, okay? So in chemistry, your line is going to stop. And you cannot guess. So if I get a value of 2, can I really report it? No, it's not in my linearity. This is my linearity in chemistry. This is my reportable range. So if I get a 2, can I report it? So what can I report? What am I going to do? No. Less than 5. Make sense? Okay. If I get a value of 20, can I report it? It's greater than 18. But a hemoglobin greater than 18, do you think the doctor really wants to know what that is? Right. So what do we have to do? You have to make a dilution. You have to dilute the specimen. So if I take 1 part of my blood and I add just simply 1 part of saline, okay, I do a 1-to-1 dilution, 1-to-2 dilution, correct? Making that simple. So then if I run my specimen, now I get a value of 11, what am I going to report? I'm sorry?
11 at 1 and 2.
Then your doctor's not going to understand your answer at all. But that's the right answer. So what do you think is the right answer? Multiply by the dilution. And you report out. Because is my answer of 11 not in my linearity? Yeah, it's between 5 and 18, so that's reportable. But if I make a dilution, I can report out the dilution. Back in the day, if you got a value of 20, you then pulled that specimen off the machine. You put 1 part of specimen, 1 part of saline or water, whatever the machine told you to do, and you got a value of 11. Went over your little calculator, you multiply it by your dilution, and then you typed in the right answer. Nowadays, that's really so slow. You put it on, the machine now knows what its linearity is. So if it gets a value greater than linearity, it does a dilution for you. You keep the diluent right on the machine, and it calculates it for you, and it spits out the right answer for you. You guys are so smart. But you gotta learn it the old way. Because CAP or ASCP still says you have to. That's just your introduction. We're going to go through this over and over and over. And we're going to start with our procedure on Friday. We're going to do a manual procedure on Friday. What I'm going to ask you is, what is the linearity of this procedure? Thursday. I'm confused. I know, I'm confused too. So Thursday. And it tells you on the procedure what the linearity is. And it tells you how to correct it if it's past linearity. Some will tell you to keep diluting and diluting and diluting until you get an answer that's within linearity. Some of you tell you can only dilute 1 to 2. At that point, you would report out greater than whatever your 1 to 2 is. Okay. So, this is important. If you're running a specimen, we're going to talk about lipids tomorrow, so we'll come up again. If you're running a specimen and your linearity is 100, and your machine says it's over range high, because it's only going to give you the number, it's over range high. First thing you're going to do is make 1 to 2 dilution. Easy, right? Run it again, it still says over range high. Okay, now you're going to make a 1 to 5 dilution. Run it through the machine, still gets the overrange. Now you're gonna make a 1 to 10 dilution. Machine still says it's overrange. Then you go to a 1 to 20 dilution. Okay? And then finally you get your answer in. That just spent 45 minutes making those solutions, running it. Alright? So you have a logbook that's required by CAP. If you get a patient that you just spent 45 minutes doing a 1 to 20 dilution on, you're going to log that in so that when the next person comes in tomorrow and they get that specimen, are they going to waste the 45 minutes doing a 1 to 20? Or are they just going to go straight to a 1 to 20? Exactly. Exactly. So, yes, ma'am.
What if the sample's no longer thick?
You're going to find out. Because maybe a 1 to 20 takes you below linearity now, right? So, cut it to a 1 to 10.
Okay, so you would just work the line
You just work backwards. Yep. Yep, just work backwards. But I'll tell you to don't change that quickly. But they can, but not that quickly. But anyway, that's for linearity. And that's just your first. You're going to hear me say linearity over and over and over. And then you have your reagent blank. So again, because you're familiar with hematology, what was your reagent blank for your hemoglobins? The Drabkin's reagent, right? Because what did you put in that cuvette? You put Drabkin's reagent and you put blood. What does the doctor want to know? The blood. So you had to take the Drabkin's out of the equation, right? So in chemistry class, did you have those little weigh boats? They still do that? And you had to weigh the boat empty first? And then you had to subtract out the boat weight of the boat. It's kind of like when you weigh your dog on the scale, right? You get on the scale with the dog and you find out, and you get on it and you're, okay, the dog's 25 pounds, well, mine's 100 pounds, so it never works. But you get my drift, right? You have to subtract out. Well, that's what your reagent is. Corrects for the reagent components. So in color, anything that's impure, anything in there. So types of specs. And I did this on the computer, I was so proud of myself. But anyway, so a single beam spec, that's what we have in there. So the light's going to shine across your monochromator. That's what that first little box is. Go into your cuvette. Okay. Then you have your then what was the next part? Photo detector, right? What are you going to read out device? Oh, please, go back. What did we do? The detector. And then the readout device, and I guess the next. I don't know. Anyway. Alright. A double beam. Here's where I'm going. So that single beam is what we did, right? Put it in there. So you had to put in your blank, right, to remove whatever the blank was. With a double beam, you have two spots at the same time. So you have your light shining through, going across your monochromator. But you have a spot where you can put the blank, and a spot where you can put the reagent. And the machine literally gets both readings and then converts. So you don't have to blank it with your little. Does that make sense? It kind of takes the reagent out. That's kind of pretty. Probably a better picture in your book. Yeah, page 106. But anyway. Okay, so types of chemistry analyzers that use a spec. You can have a continuous flow analyzer. Oh, maybe glue and chalk just don't work, does it? Continuous flow analyzers. Specimens and reagents are loaded on the instrument. Change can be made until the instrument reaches a certain point. Single test, usually about 40 per hour. They're very fast? 40 per hour? No, let's look down next one. 360 to 720. Okay, continuous flow or batch analyzer. So basically what you're doing is you have a wheel. It's kind of like our CA2, our Cobas mirror. You have a wheel, okay, you're going to load up those patients, you're going to push go, and you can't do anything to it for 45 minutes. That's why your lab partners are going to be mad if you push go and they haven't put their stuff on, right? Okay, batch analyzer. Simultaneous multiple analyzers. This is, it was called a SMAC, CMA, CAMC, C for chemistry. And you had a SMAC 6 or a SMAC 12. That was the old terminology. Now we call it like a Chem 8, Chem 7, Chem 8. But it used to be like a SMAC, SMA. Liquids are pumped through the system continuously. Again, 6 to 12 tests simultaneously, 360 to 720 per hour. Pretty good. But you remember, if you've probably seen pictures of the old computers, like the computer that War Tennis used in the old Disney flick. How big were those computers? You ever watch War Games? You ever seen it? The whole room, right? How big are our computers now? Right? This SMA literally took the entire chemistry room. It was huge, floor to ceiling, and tubing, okay? Nightmare when it went down. This was the very first chemistry analyzer I ever ran, and it was huge. It would literally take the whole wall, floor to ceiling, lots of tubing. And if you got a fibrin clot in there, you were not a happy camper. Okay? Centrifugal analyzers, NASA, batch analyzer mixes reagents and uses centrifugal force to mix them. Okay? Discrete analyzer, when I became, so SMA when I was an MLT, ACA when I was an MT, so I had progressed a little bit. ACA, you know your cuvettes are test tubes. ACA, your cuvette was a little plastic bag, a little plastic Ziploc bag, if you will, okay? And it would squirt in the reagent, squirt in the blood, and go through the machine, and the machine would squishy to mix it up, and then it would go to another part of the machine that would squish it and form your little cuvette sail, shine a light through it, give you your reading, and then it spit out, okay? So, what did you have at the end of the day? A great big huge waste tub full of pieces of plastic cuvettes. And they were all slimy with this oil because when they squished it together, they wanted to have that oil so they get better light transfer. Real fun. Real fun. Dry chemical analyzers, kind of where we went after ACA. Used to be called Kodak, now it's called Vitros, and they use dry reagent slides. So, one at a time, okay, you would, well, the Vitros was one at a time, but the Kodak would do more at a time. So you had little, they were about the size of a bit bigger than a postage stamp, okay? And it was dry, and then the machine would come along and literally put a drop of blood on this dry, that had the reagent in the dry filter paper. And then it would run through and then it would read it. And it would spit out that little piece of paper, that little cartridge. Disadvantage on this one, you would not believe the amount of room it would take in a storeroom to store all those little paper cartridges. And then think about how much waste you had to throw away. And again, it's biohazard waste. Biohazard waste you pay for. You have to pay to have them come together. Okay? Random access can be programmed to perform any test on any specimen at any time. Awesome. Reagents are all loaded up. You get a specimen, you put it on, push go. You run whatever it wants. Get another specimen in, walk over the machine, put it on the machine, push go. Reads the barcode, does the specimen, you get the result. What is your waste? Yes.
Having all of those analyzed though, but now taking it from room and even paper.
Do what, I'm sorry?
You would have to have every single analyte, one that's even more room than just paper and things like that. That seems like that would take a lot of room, having each analyte from every test.
No. There, well, if you had one, probably many bigger than this desk, right? Colas? You know Colas? You remember, it's right behind you when you sit.
Yeah.
One probably is that big, and then we have two side by side.
Mhm.
Because if you ever have a major analyzer, you always have to have a backup. And so we have two sides, so it's not that big. And the reagents, liquid reagents, and they come in cartridges and you just load them on.
So it's not gonna be like a normal, everyone's got these big boxes of reagents.
Not anymore.
Okay.
Now they're kind of small little cartridges. You've seen them from one.
Mhm.
They're just small little cartridges. Okay. Most of it's liquid waste can go down the drain. You have to pay for that. Right? Now, the Cobas mirror does have individual cuvettes, so it does generate that kind of waste, and individual tips, just like I was told to tell you earlier. We had the machine we had before, which I don't know why we ever got rid of, called it Hitachi's. It could actually pierce the cap, go in, get the sample, and the cuvettes were washed, just like my CA240, so all you had was liquid. Man, then we went kind of backwards. We went to a machine where you had to pop the forks. Yeah, and stuff, so we kind of went backwards. I'm sure it was some deal that some, you know, sales rep made us or something, I don't know. But anyway, so that's kind of how things progress. From doing one at a time to lots of waste to a little less waste. Chemistry in a nutshell. Okay, who wants to go first? Your turn. Here we go. I'll get out of your way. Now, what your job is going to be, as there's going to be a good audience, and you're just going to sit and listen, okay? When it's all done, I'm going to run to the copy machine, and I'm going to make you a copy of the answers. Well, not the answers, but what you need to know for your test. Okay?
But I didn't forget because I don't have any colors on the
That's okay. That's okay.
Okay,
Or can you pull it up? Have it on a flash drive?
yeah, I can pull it up.
Either. Just show it up there.
Okay.
So, I don't know if you want computer or Elmo, but we can switch back and forth. And so, I'm just gonna be sitting back there and I'm gonna be listening to see if you have to make things listen. You want the Elmo one?
I just wrote a report. Do they actually need to be able to see the?
You want, I'm sorry?
I just wrote a report. Do they actually need to be able to see the other thing? Because if so, then I
Yeah, if you have a picture or anything, do you have a picture or anything they can see?
Let me email it to myself.
Okay, so let somebody else know while you're doing that?
Yeah.
Okay. Somebody else?
I have
your
a
brain.
I
Okay. I'll say Not scary. It's okay. You get 10 points for just being here. Move your stuff out of the way so I don't trip on it. Or try not to anyway. I'm not that stable. There you go.
Can I tell them what the test actually is?
Yeah, tell them whatever you want to tell them.
Okay. Okay, I have serum protein electrophoresis. This test measures specific proteins in the blood to help identify some diseases. You can see albumin proteins and 4 types of globulin proteins on this test report. Every type of protein has its own implication, and if raised, it has a different meaning. The principle of operation is fresh blood in a SST/gold top. The technician places the blood sample on a special paper and applies an electric current. The proteins move on the paper and form bands that show amount of each protein. Examples of analyzed one is albumin, and we have four globulins: alpha 1, alpha 2, beta, and gamma. The advantages or inexpensive equipment is cheap to run, it's commercially produced gel, and multiple samples in parallel on the same gel. Disadvantages is low resolution, it's time consuming and laborious, which means gel preparation, separation, staining, destaining, and gel drying. And the gel must be treated to visualize.
Yep, and you're gonna get an entire PowerPoint on SBE. She just gave you a rundown. So it's exactly what she said. You literally put a specimen on a gel, and the gel, and then you give an electric current, and the particles move. Okay, they separate out. Your different proteins separate out, and then you put them on a densitometer that reads the bands, and it tells you the value of each one of your proteins. Okay, and like she said, as far as your advantages, it was cost effective, but I think your disadvantages said time consuming.
Yeah.
So it would take one tech, okay, 6 to 8 hours to do one plate of maybe 20 specimens. So is that it's not very cost effective. You know, I mean, it's really expensive in that respect. I hated doing it. I was part-time, and so I didn't get to do it very often. And you had to get your specimen in this itty-bitty little well with this itty-bitty little pipette. You had to have a good steady hand, and then once you got it all loaded up, and then it would migrate for so long, and then you would stop it, and then you'd have to stain it, and then you had to dry it, and you had to do this whole process. Then you had to put it on densitometer and read it, and then you had to give it to the pathologist only for him to look at it and go, I don't like it. So I didn't like it. Because if you touch the gel in any way other than its little well, it would skew the result because it would migrate differently. So it was very, very touchy, very touchy. Very good, very good. But you get a whole lecture on SBE. You'll know what all the little bands are and what falls in all those little bands and everything. So can I get the immunoelectrophoresis person next, because you technically follow this?
That was me.
That was you? Oh, well, we went backwards then. There you go. No, actually, we went the right way this time.
Can I get rid of this?
Oh, yeah.
Nice. Sorry. Email inspection.
Your email's a lot different than ours.
Just ask me to like set up like one of the little questions or like,
Set it up now? Do you just have to answer a question? I don't know.
If you guys want my bills, have at it.
You don't have to do that. I think just choose another way you could bypass it.
I think it still looks good as long as it goes grayed out.
Yeah.
Yes. Sorry.
There you go.
Okay. I'm sorry, I needed it over here so I can see the rest of
That's
it.
okay, that's okay.
So I had immuno,
Electrophoresis.
was it just immunoelectrophoresis?
Mhm.
This is one of the basic. There's going to be a battery out here instead of two. This is the gel plate. Here's the walls that you same thing with hers.
Yes, yes, hers would look exactly the same.
The principle and method is you add a serum to the reactant, or a serum or a reactant to the legs. But for mine, you would need a trough underneath each of them where you can add the this is where you're going to put the known antibiotics. And you're going to need to watch out for the vision. Electrophoresis part of this is going to separate the serum. Then after which you can draw it out. It takes about, I think it's 12 to 48 hours.
And it takes a long time.
12 to 48 hours for it to diffuse into the gel and react. What you're going to end up with is visible lines. During the electrophoresis process, it's still all you're seeing is the gel. It's not a visible process. Once the interactions between the antibodies and the antigens happen, there's a visible line, usually a curve of some kind, and that's
Look like little eyelashes.
And that's just indicating that there was a reaction that happened, and how great the reaction is. I believe I read somewhere that the darker the line, the greater the reaction.
Right, exactly.
The examples of analytes, the only ones that I could find were blood and urine.
Exactly right.
And disadvantages and advantages are, the advantages, you only have a specific protein can be analyzed fairly quickly, both qualitatively and quantitatively, in a relatively large number of samples. The disadvantage is it's based on the formation of an antigen-antibody precipitate. So if you don't see that precipitate, it may or may not be
Yep,
active.
your pathologist sends you back and says to do it again. So here's the rundown. She's going to do a sample. She's going to do the electrophoresis. She's going to separate it out into its 5 major components: albumin, alpha 1, alpha 2, beta, and gamma. If the gamma fraction is elevated, the gamma fraction of your SPE are your antibodies. I know you're just now getting into serology, so I don't know how much of that you know, okay? But you have 5 different classes of antibodies. If your gamma region is elevated, that means you have an increase in amount of antibodies. So what is that telling the doctor? You have a lot of antibodies. You have an infection going on or some kind of process, disease process. So then she would hand the specimen to her, and she would say, okay, the gamma fraction is elevated. You need to separate it out into those 5 antibodies so that we know what's going on with that patient. Because just telling the doctor that the gamma fraction is elevated means really nothing. Which of the 5 is elevated?
This is what you're looking for.
And that's what it'll look like when you put it on the densitometer, yes. So you guys are going to actually do this procedure in serology, okay? Because Jean has a way of doing it on an agar plate, okay? So you don't need the electrophoresis gel. And it's called an Octoloni procedure, and you guys are going to look for those little eyelashes. It's actually a pretty cool little procedure, and she does it with you in a little petri plate. So it kind of goes along with some things that you learn in serology.
Fun fact, augers seaweed goo.
Yes, that's right. That's exactly right. So you can turn that off and do whatever. Very good. Next.
Okay, I have the point of care glucometer. Well, I have the point of care, but she asked me to do the glucometer. That's the handheld. Instead of a large analyzer, this is a low complexity test, so nurses or CNAs, or actually some people can do them at home. So you can check your glucose level. It requires a very small amount of blood instead of an invasive test where we actually have to stick a patient. It's just a finger stick with 1 drop of blood. It goes on a strip and then is inserted in the end of the glucometer. It goes through, it has a few different QC methods though. Just like anything that's run in the lab, it has to have a QC. So the strip, every time a patient is tested, the strip, it runs a QC. But then there's QCs that have to be done weekly, monthly, internal QCs with the software, and then the QCs, the weekly and monthly, that have to be done by the nurse or whatever staff member is using it. The glucose isn't the only thing that can be tested with the point of care. It can be protimes, ketones, lactates, chem 8s, blood gas. There's plenty of other point of care methods. The advantages is it's fast, it requires very little blood, so it's not invasive. It's portable, RNs and CNAs can use them. The disadvantages, however, are it's not as sensitive, so if it's above a certain number, the specimen has to be checked through a normal venous stick.
Yeah, you can't do a dilution.
Yeah, you can't do a dilution. It's limited, so you can't, unlike the large chemistry analyzers, you can only do 1 test at a time, and those are limited to the glucose, proton, ketones, and etc. It's also a major disadvantage is it's dependent on other departments to complete the QC, which is a big issue.
Yeah.
It's a big issue. So, and then disadvantage, whole blood doesn't give the opportunity to see if the specimen is hemolyzed, which, as we know, it can affect the potassium. So when you're doing a chem 8, that can be affected. And oftentimes squeezing the finger can cause hemolysis.
So the third one over on the right, I have that one. We're going to use that one tomorrow. And then the first one on the bottom, I have one of those.
And those look like home. Those are like home ones.
Exactly.
The ones that are used in the hospitals are larger. They're docked, and so they can.
And they have barcode reading ability so that you
Mhm.
can read the barcode on the patient's band so that you're actually identifying the patient. But I just have the ones
Yeah.
that are kind of little brain. So, yep, very good, very good.
Okay, I have the ion selective electrode. These are a couple of the pictures. These are going to be your the probes that actually go into it. This is a probe with the solution. It's got a sorry, I'm gonna say it wrong. It's a selectable membrane in here that it goes into a solution that has your ions that are dissolved in the solution, and it basically it's sorry.
Anyway, it's a sensor that measures the activity of an ion dissolved in a solution and converts it into an electrical potential, or basically monitors the electrical charge of it. There are about 4 main types of them. They measure ions, so cations, anions. They have glass one, a crystalline membranes, ion exchange resin membranes. They have enzyme electrodes. They also came up with some metal ones, I believe, recently, but those aren't as common as what you're going to see here. We measure specific ions, so this is, like I said, this is some of the analytes. I couldn't figure out how the pluses. Those are cations, like hydrogen, sodium, stuff like that. And they do anions as well. Some of the advantages are they don't cost as much. It's a quick test. It doesn't contaminate the background. I'm sorry. It's not affected by color, and it's not destructive to the analyte. Some of the disadvantages are precision. If you're off by your measurements at all, it causes some really big problems in your results. You can have interference by different ions. Electrodes are fragile and they have a limited shelf life.
Very good. So we do ISEs for our sodium, potassium, chloride, and CO2 in the lab. And the one we had was a membrane. And so if you can imagine, you had to take this little thin membrane and you had to put it on the bottom of the electrode. And then you had to use this tool to push on this little rubber band to seal that membrane onto, and let me tell you, you got a little bit off and it didn't like it. And the bad thing about with the ion selective electrode, it drifts very easily. It will drift. And you're not exactly sure it's drifted until you start seeing, well, why is everybody's values all of a sudden low? Why is everybody's sodium like 133 when normal's 135? So you have to go back and recalibrate it, and then you have to go back and rerun the last 3 specimens to see if they truly changed. And if they did, guess what you do? You go back to the last good QC value. So that was the hard part with ISEs.
And I ended up watching a YouTube video on how they did the test because I didn't really understand what they were saying on the internet. They actually had it mixing while they were doing it, like a little mixing rod. Does that help with the precision, kind of like what you're saying?
It's just a different methodology.
Oh, okay.
It's just some have mixers and some do not. Some will have just like a little bar that will,
that's
that will
what
mix.
he had.
Yeah,
Mhm.
yeah. Now, my CA240 came with an ISE module, but I knew how hard they were to maintain. And with us only running them for 3 weeks out of the year, I knew there was no way I'd have to be changing them every single year, and that just would be way too costly. So I went ahead and sold it back. I sold them back the ISE portion, so we don't have that in our CA240. Again, it would have been a nightmare, and I thought there would have been no reason to pay the extra $10,000 for that module if we couldn't probably use it 1 year and then be able not to maintain it. So, but we have other stuff. So that's good. Very good. Very good. Okay. Next. You gonna put it on the Elmo?
Yeah.
Then that little clicker thing, just change it to. Yeah, you should be able to change it to, one is computer and the other I think is a video or something.
Video?
Yeah, there you go. I don't know what's going on with it, but I think that thing's turned. You see the Elmo of that head?
Yeah.
You just click it down, straight down, I think it gets turned. No. Just the part your hand's on. Just click it towards you. There you go.
Okay.
There you go.
Alright. Okay. I had osmometry. Specifically, I just did freezing point osmometer. That's what's more common in the lab.
Yep.
Let's see. Okay. Now, osmometer is used to measure the concentration of solute particles in the solution. They measure freezing point depression or vapor pressure depression. Results are measured in millimole per kilogram units.
Millimoles.
Okay. The method is a sample. Is that clear?
Yeah, you're fine.
Okay. The sample in a small tube is lowered into a chamber with cold refrigerant refrigerant circulating from a cooling unit. A thermistor is immersed in the sample. To measure temperature, a wire is used to gently stir the stirring wheel. Is to gently stir the sample until it is cooled to several degrees below its freezing point. The analytes that are analyzed are the dissolved particles in urine and serum. The advantages really outweigh the disadvantages. Osmometers are useful for determining the total concentration of dissolved salts and sugars in blood or urine samples. Osmometry is also useful in determining the molecular weight of unknown compounds and polymers. Osmometers are very fast and accurate. Test times are less than a minute. Sample repeatability is in slight range. They are very simple to use and they only require a small sample. A disadvantage, they are not used for batching, only single use at a time, but because they only take less than a minute to use, it's kind of not really that big of a deal. Simple but frequent maintenance is required. You have to do daily checks of the coolant level, bath temperature, and calibration.
Very good. So basically what you are doing, you are taking a small pipette, okay? You're putting your urine in that small pipette. You are lowering it into a cooling solution that's going to supercool it. And then it's going to trigger it to freeze instantly. And the machine can measure the temperature in which that freezes. So think about it this way. When it gets cold outside, drops below 32 degrees, what do they do to the roads? When it snows? Salt, right? And if we add salt to the road, what does it do? Drops the freezing point of the liquid, right? So the more dissolved substance you have in a liquid, the cooler it has to get to freeze. So what is this telling the doctor? If it takes a lot to get it to freeze, you have a lot of stuff in your urine. Does that make sense? You're going to learn about this in urinalysis and chemistry, so it's going to kind of run simultaneously. What we do more in chemistry, urinalysis, yes, we need to know what's in the urine, but with chemistry, you tend to run a urine and a serum at the same time because we can tell that if there's a big fluctuation between what's in your serum and what's in your urine can give us a warning as that you have some problems with your brain damage. So like in a car accident or some kind of a disease process going on. That's the big thing it kicks us into. Where Jean's going to go into more the osmometry with the urine and the kidneys, with chemistry we're more worried about brain function because the difference between the two can help us with brain function.
So if you're kicking more out and it's in the urine, if your nauseous and
If it's higher in your blood, then yes, then exactly. So if your blood levels are higher, it's not going through, and so it can be a problem with the blood-brain barrier. Yep, very good. Next. It's a little chilly in here inside.
Okay. So I had chemiluminescence, and one of the analyzers that uses that process is the Advia Centaur XP. There's a picture. You can see the status lights, and then down below that is the refrigerated reagent pads, and then you have the sample rack, the stat port, the control monitor, and the sample track. Examples of what it tests for, it measures the quantity of over 80 different assays in patient serum, plasma, or urine. So there's a whole bunch of them, there's over 80. So I try to stick with some things that we already learned about. So it can help diagnose anemia, by looking for active B12, ferritin, folate, or vitamin B12. It can help diagnose diabetes by looking for C-peptide or insulin. Bone metabolism by looking for vitamin D total. Metabolic processes by looking for cortisol and homocysteine. And it can look at reproductive endocrinology by measuring HCG, testosterone, and progesterone. So how chemiluminescence works is it's the reduction of light from a chemical reaction. For example, this analyzer would work to detect insulin by distributing 25 microliters of patient sample into a cuvette, adding 50 microliters of light reagent to the cuvette and incubating it for 5 minutes. And then it adds a solid phase to the cuvette too. And what those are is they come in that reagent ready pack for the specific test. So they're all loaded into that. It separates, aspirates, and washes the cuvettes with reagent water. And then it dispenses 300 microliters each of acid reagent and base reagent to initiate the chemiluminescence reaction. There's a direct relationship between the quantity of insulin found in the patient sample and the amount of reactive light units sensed by the Avia Centaur XP using the chemiluminescence process.
Did it tell you what the solid phase was? Did it tell you what it used?
No.
It's kind of like a rust.
Is it?
It's like a rust, yeah.
It showed in the video how you have to mix it well.
Mm-hmm.
But then once you get it into the analyzer, it's got an onboard rocking system
Right,
that keeps
right.
it going for you. So advantages, it only takes 10 to 200 microliters of patient sample, depending on what test you're running. It can do up to 240 tests an hour. Samples can be loaded at any time, even when the system is running. It only takes 18 minutes to generate a first result, and then results come every 15 seconds after that. It holds over 30 different reagent ready packs on board. Supplies can be replenished at any time, even while the system is running. And it has a stat port that allows stat samples to be run first, even if you already have other samples loaded. Some disadvantages is it can test for many assays, but it can't test for everything. If you don't have access to a drain, you have to empty the waste containers and fill the reagent water by yourself, which doesn't sound like a big deal, but Barb and I were talking that waste is very toxic, so you probably wouldn't want to deal with it. Samples must be put into a sample rack. Each sample rack only holds 5 tubes, and they all have to be the same type of tube. So you gotta make sure that they're the same type. You can't put different types in there. The reagent ready packs only process 50 to 100 tests, so depending on how much you're running, you have to change them frequently. And another thing we were talking about is it generates a lot of biohazard is waste, and then you have to pay for that because it uses a lot of cuvette tips and stuff. Very good.
Is that the same method used for like the Petros and the Architect? Is that all the same method for all those animals?
I'm not familiar with the architect. And the
It
only
I mean, everything sounds similar. I just don't
Yeah.
know about that.
And you brought up with the XP, we didn't have an XP. And so WARS, once you loaded it on and pushed go, you could not touch it. You could not load up anything, but that must be a new change that they made. People probably complained, it's like, okay, it's running for 45 minutes, but I got a stat. So that must have obviously been a change that they've made. But we don't have the Centaur anymore. Because I keep track of safety data sheets, I also have to keep track of how many carcinogens we have in the lab, reproductive toxins and acute toxins. And at that time, when we had the Centaur, we had 20 acute toxins. When we got rid of the Centaur, we went down to 1. So that was a big plus with the hospital. As soon as they read that, they went, oh, okay, great. You know, we're making less horrible waste. So what are we doing?
I'm doing
Oh,
enzyme amino acids. I just brought it up. Hold on.
and this is one you're going to do more in serology than you are in chemistry. This is more of a serology thing too.
Just a view image, yeah.
You
Oh,
see
on
the
the-
yeah. see it.
Pull down natural.
Yeah. And Jean's gonna go over this in great detail with you as far as the sandwiching between all that too, so.
The immunoassay is a technique which incorporates the binding reaction of a target substance or the antigen with an antibody. Antibodies are basically immunoglobulins that bind to different natural and synthetic antigens in the body, such as carbohydrates, lipids, proteins, and nucleic acids. I think usually it's proteins. If these antibodies are high enough quality, they'll bind to the chemical and only to this chemical, which is the antigen. And then in turn, the antibodies are bound to a detectable indicator, such as a fluorescent chemical or a radioactive isotope, and that causes changes in color or produces light so that you can measure what you're trying to look for. The immunoassays can be competitive, non-competitive, heterogeneous, or homogeneous, and the specific methodology of them is in here and a little over my head.
Yeah.
So I'm just going to show you 2 examples. These are, I think, these are competitive. Here's your antibody, and you take your labeled antigen along with a regular antigen, and they compete for the reaction with the antibody, and then you wash it, and whatever is left over is what you measure. Or you can take your antigen and add labels to the antibodies, and then they'll attach to the antigen, which is, I guess it's connected to this solid plate, and you wash it, and you can measure the antibody instead of the antigen, whatever you're looking for. I will tell you about the ELISA method is the most common, I believe. You can see what I'm doing. I think the ELISA one is heterogeneous and non-competitive, maybe?
Usually not.
Okay, so anyway. It is the most common type of immunoassay. It's a specially treated plate coated with antibodies for a chemical. And then samples are added. Hold on. Okay. The first set of the antibodies binds the chemical to the plate, and then the plate is washed so that all the chemicals except the bound target chemical are removed. Right here, and that's your target analyte. That's what you want there. Then antibodies are added against the first set of antibodies, which are bound to an enzyme. The second antibody binds to the first, and the plate is washed again. And finally, a chemical is added to the sample, which is catalyzed by the enzyme to produce a colored product. And then the amount of color can be read by a spectrophotometer. Examples of analytes. The antibodies are the reagents. So blood, urine, you can test like qualitative, so it would be positive or negative results, or quantitative, so you can measure the amount with the assays. And one example of qualitative is a pregnancy test. You can measure for antigens on like streptococcus and cerebrospinal fluid, like with patients with meningitis too. And also antigens associated with organisms that are difficult to culture, like hepatitis B, chlamydia, or like viral hepatitis, HIV, and Lyme disease. You can use immunoassays to diagnose those too. Advantages and disadvantages. The major advantage, it can can detect small amounts of protein in blood, urine, and just about anything else you want to try. And they're cheap compared to other ways of analyzing a sample, and can be designed to be very easy to use. So they can be sold as single-use diagnostic tests, like pregnancy tests. They're $1,
Right.
and
Yep.
they're effective.
And it's wave testing, which means anybody can do it. You don't have to have a technical, be a doctor or a tech or anything.
Like when you add the enzyme and it has the color producing or light producing thing, like that's what you're reading here is the color, and that's like the line on the pregnancy test
Exactly. Exactly.
for positive or negative.
So the tests in serology are very easy. You take the cartridge, add 3-5 drops of urine, and you can read a color at the end. But unfortunately, she's going to force you to know all of this stuff and what binds with what. So with serology, what's kind of difficult is because you were talking antigens, antibodies. But sometimes it's the antibody you're looking for, sometimes it's the antigen you're looking for. And so that's what you got to keep in mind when you're going through serology is what is presenting with the antibody and what is presenting with the antigen. Okay, so it's a little complicated because it's not the same with every test. When you get to blood bank, I need you to know the difference between antigens and antibodies. But what makes it so much easier is in blood bank, the antigen is always the red cell, and the antibody is always the plasma. But that's not the case in serology. Very good.
A disadvantage is you have to have good quality antibodies,
Yeah,
or it won't work.
right. Very good.
And no, that's it.
Next. Do my chromatography people want to go?
I'll go first. Basically, chromatography is just a chemical analysis that uses either the gas chromatographer and the liquid chromatographer are the same, correct?
Well, only difference is that you have to make the liquid gas and
Right.
then do the other one, yes.
Okay. First,
Did you do both, or would you?
No, Chris did
Okay,
liquid.
okay.
I did gas.
Okay.
Okay, first, a tiny sample of the mixture is placed inside of the machine, which, if you can see, is done by a syringe on number 4. The components in the mixture are heated and then instantly vaporized. Next, you add a carrier, which is the eluent, which is usually helium or hydrogen. And it's simply just a neutral gas designed to help the gases in our sample move through the column. In this case, the column is a thin glass or metal tube, usually filled with a liquid that is at a high boiling point, or sometimes it's a gel or an absorbent solid. So as the mixture travels through the column there, it's absorbed and separates into each individual components. So each component emerges in turn from the end of the column and moves past the electronic detector. And then the electronic detector identifies it and prints out a peak on a chart. And the final chart has a series of peaks that correspond to all the substances in the mixture. Gas chromatography, sometimes called vapor phase chromatography. One of the big advantages is that it works with tiny samples, and you only have to have a very small, low concentration. I know a lot of it's used in forensic science and
CSI.
drug and pollution testing, like in pollution testing, like in the air, or samples like in the water. So that's just kind of a rundown of the different components that it goes through.
Very good. Very good. She made it easy for Mr. Liquid.
Coincidentally, when I look back at my sheet from the day we assigned them, I do have gas in it.
Oh, all right, so you did the same one? All right, so basically they
I
are
have
the
the
same.
paper from the
She
first
really did a
one.
good job, and so they basically are the same. Did you have anything to add that was different than hers?
Percent chance of decomposition with the disadvantage because whenever it's vaporized, it cannot be used again.
Correct.
Example of gases used are the nitrogen with helium, nitrogen with argon.
Argon. Yeah.
Noble gases can be used. Low cost and longer life of the
Right,
system.
right. The really main difference between the two, and she did a really good job of explaining it, is if it was liquid, it would still be separating it out. So it's just like when you're trying to find arsenic in somebody's blood and it's going to make a particular spike as you're moving it out. The only difference between the liquid and the gas is, again, with the gas you have to make it volatile. So, but other than that, the principles are the same. Yeah, very good. Come on, we're almost done. Nephelometry, fluorometry, atomic absorption.
I guess I'll go. I'm nephelometry.
So I have nephelometry. I don't know, it seems like a pretty simple
It's very simple.
thing to do. So basically you have, and there's several different things. This is like a simplified version, but they do have big machines. I write on one, it will hold about up to 28 samples. But this is just like a simple thing. So basically you have your laser or your light, and then it goes through your solution, which is usually, they test different analytes for health. They do antibody isotopes, or like the antigen, or they can also do other organic materials and basically just test the solubility of those. So you have the light, and it goes through your solution, which is just in a cuvette, and then it's got, it just shows one here, but the machines also have like several detectors, and it's basically, what you do is the antibody used in immunology usually is the reagent, and it's combined with the patient sample, and if the antigen is present, the antigen-antibody complexes will form a precipitate and it will fall out of solution, which is, jumping ahead, is one of the disadvantages, they said, because if there's too many antigens or antibodies in there, they will fall out of solution, and then it will actually kind of skew the results. So basically, what it does is it's a method to detect particles in liquid samples. The principle is to measure forwarded scattered light, which is what all this is. So it scatters around and then it goes through the detectors, and that's what's measured and reported. Then I found two different types of nephelometry. There's the endpoint nephelometry and kinetic nephelometry. The endpoint nephelometry allows it measures like the whole reaction. It goes through completion, and that's what I was talking about, the large particles that they will fall out of solution, and it will cause a false scatter because they fall all the way down, and then the light won't actually, like the precipitate will fall down here, and then the light won't get through all of them. Then they came up with another one. It's called kinetic nephelometry, and it measures the rate of scatter right after the reagent is added instead of waiting. So the rate of change is directly related to the amount of antigen present. So the more antigen you have, the more change in light you're going to have, so the higher the number will be. So it measures the different antigens or antibodies, IgM, IgG concentration. So.
Very good. So basically, when I talked about the spec, you had a beam of light going through a cuvette, and you had a readout on the one side, right? With this being different, because you were using, like, your hemoglobin was dissolved, this you're having actually little particles. So the light is gonna hit the particle, and then the light is gonna scatter in different places. So you have to have many detectors. Does that make sense? Because you're catching the scattering of the light, not just a single beam going through. So scattering of the light is exactly what you want to remember with nephelometry. Very good.
Hey Lauren, I also have the safety thing. Do you want that now or okay?
You're going to learn a lot about nephelometry and serology too. That's more than serology.
I have photometry, and at first I had found a machine that is just hand monitoring, and it quantitates the low levels of DNA samples accurately. It can also be used to detect trace metals in water, because I have to go back and look at that, you said that. And then it's used to measure the parameters of fluorescence and the intensity and wavelength that's distributed by the spectrum after excitation by spectrum of light that's red. And it also measures the amount of the electromagnetic radiation produced by the pulses of electromagnetic radiation emitted in a water sample, and that's how you can get the trace metals. And then there's the one machine that I have found that does the DNA and RNA tests, and they're done on a Quantus fluorometer, is what's called, and that's next-gen sequencing. The main advantages of fluorometry is the specificity and sensitivity that you can get off of it. And the disadvantages is that it's very sensitive to environmental changes, also changes in pH affect the availability of electrons, and the temperature causes a loss of energy.
That's very good. You're just measuring fluorescence, and you're right, it's 1,000 times more sensitive than a spec. 1,000 times. But again, that cockroach runs across your sample. You got it. Very good, yes. You want video or you want computer?
I hit video
There you go.
3 times. So I had atomic absorption, and here's the schematic. You have a light source, which emits light of a specific frequency. It's usually a hollow cathode lamp or an electrodeless discharge lamp. And then you have the absorption cell, which is the flame. And by using the flame, the sample is converted into a fine mist and then causes the sample to turn into its atoms. The monochromator, the light is dispersed. It's a light dispersion device that is used to select the specific wavelength of light that is then absorbed by the sample and excludes other wavelengths. And then you have the detector, which measures the intensity of the light and amplifies the signal, and then the screen that tells you what the results are. The principle of atomic absorption is it's an analytical technique that measures the concentration of an element by measuring the amount of light that is absorbed when it passes through a cloud of atom elements. Basically, it's the measure of light energy that is absorbed by a given sample and shown by the change of wavelength that is given off by the light.
There's several different analytes analyzed. The clinical, basically, it's done by analyzing biological fluids, and it's used to find metals that can cause diseases. And we typically use whole blood, plasma, urine, brain tissue, liver tissue, semen, and even the umbilical cord. It can also be used for pharmaceuticals, water, and foods to find different levels of metal in that. The advantages, it's a high samples, you can put a lot of samples in through once. It's easy to use, it's high precision, and it's relatively inexpensive. The disadvantages is only solutions can be analyzed, it's less sensitivity compared to a graphite furnace. A relatively large sample is required 1 to 3 milliliters, and then you can have problems with the refractory elements inside of the system.
And do we want flame in the laboratory
No.
anymore? Yes. So we actually had one, and you did flame it. You would put it in the flame and it would measure. But yep, that had to go away when we couldn't have gas and flame in the lab anymore. So we don't do it in the clinical lab. So very good, very good, very good. Okay, any question? Okay. So in blood bank, you'll have 2 of those. But they're equally as difficult. Okay, so the next thing we need to do is your safety data sheets. So did everybody grab a safety data sheet? You have a worksheet in your syllabus. And you're just basically, you've done it before, so it shouldn't be too hard. Just a couple things I want to show you. I'm sorry? Oh, go ahead. And this isn't due till tomorrow, and you can work on it in lab.